Hello and welcome to the EMC Live webinar, Smart Grid EMC Standards Harmonization. My name is Belinda Stachukevich and I'm the editor of Interference Technology, the creator of EMC Live. EMC Live is a brand new online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Jerry Ramy. Jerry is a 31-year veteran of the EMC test and measurement equipment business. He's secretary of the ANSI ASCC 63 Committee on EMC, a member of the American Radio Relay League EMC Committee, 2011 Distinguished Lecturer for the IEEE EMC Society on the Smart Grid, a member of the SGIP2 EMI Issues Working Group, and Vice Chair of the IEEE Power and Energy Society Substation C2 Working Group. He can be reached at jramy@arctechnical.com. This webinar is one of many. To check out our others, visit emclive2014.com. A recording of this webinar will be available on our website shortly. This webinar will be interactive. You will be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right corner of your screen. If at any time you have questions, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We will present the topic for 35 minutes to 45 minutes and questions if we can get to them. Now Jerry will begin the presentation.
Thank you. Can everybody see my screen? It should be a green title screen.
Yep, looks good.
I'm Jerry Ramy of ARC Technical Resources. This is a Smart Grid EMC Standards Harmonization. I just want to mention the funding was provided by the American Radio Relay League Spectrum Defense Fund. In the mid-1960s, new solid-state analog components in protective relays were failing in substations. They were traced to oscillating voltages created from normal switching operations, not high current faults. Oscillatory surge withstand capability, or SWAC test, simulated those events. It's first codified in the mid-70s as ANSI IEEE C37.90.1, then a trial use standard. Test simulates oscillatory voltage transients up to a megahertz at 5 kV or more on the control wiring that resulted from these switching operations. And of course, the equipment manufacturers at that time had to begin designing their equipment for immunity to these simulations if they wanted to continue to sell to the utilities. In the late 70s, the false tripping of a transformer differential protective relay knocked a 380 megawatt steam turbine generator offline. It's caused by an employee keying a portable radio transceiver less than a meter from a protective relay rack. ANSI IEEE 37.90.2 simulated this radiated RF field for testing immunity of protective relays to this threat. And it was published as a trial use standard in December of '87. At only 10 volts per meter with AM modulation. The guy backed into the rack with the radio in his pocket, I was told. Also in the late 70s, a false tripping of a barge-mounted peaking gas turbine generator occurred at the Gowanus substation in New York. It's traced to an auxiliary interlocking relay with very low battery drain in case the plant lost power. The relay's pulling coil had very high inductance, 2 Henrys, to produce a strong magnetic field with very little excitation current. When the external circuit would attempt to de-energize this relay coil, the inductance and the stray capacitance control panel wiring created an LC circuit with discharging voltages up to 4 kV DC peak on the control wiring and rise times of 5 nanoseconds, repetitions rates to 2.5 or 5 kilohertz or higher. Simulation of this burst waveform was first published as IEEE standard C37.90.1 in the early 80s as electrical fast transient immunity testing for protective relays, and was cited in IEEE 1613 in 2003 for the evaluation of utility communications equipment. In August of 1997, operators Haddam Neck Nuclear Power Plant ordered photographs taken of the inside of the control cabinets for training purposes. The flash photography of the control panel interiors led to the false activation of the halon gas fire suppression system. The ceiling was blown out and collapsed in a deafening roar, and the evacuation of the control room was required. Southern Illinois on September 25th of 2001, solid-state relay controller interrupts a transmission line for no apparent reason. The guy's 470 megahertz handheld radio was found to be the cause. Indian Point, New York, March 23, 2008. Emergency shutdown of the reactor at the Indian Point nuclear power plant was caused by signals from a worker's digital camera. Federal regulators said that a Kodak C340 digital zoom camera too close to the control panel interfered with a boiler pump controller that provides water to 4 steam generators. It blinked off without setting off an alarm and starved the reactors of water. Quote, the direct cause was radio frequency interference from the camera, said the NRC. All that had to happen was for the camera to be on. More stringent specifications of the control equipment was clearly called for, since normal operation of this plant was to be susceptible to upset by nearby consumer electronics. This indicates an insufficient compatibility margin. That's between the emissions levels from the cameras or other interference sources nearby and the susceptibility thresholds of the controls and their wiring in the cabinets. The advent of cell phones and tablets operating above a gigahertz at frequencies above these older IEEE standards. New RF hazards have now arisen. There has been reports of false operation of protective relays when the access door was open for maintenance. Somebody's nearby cell phone and tablet autonomously transmits. This testing gap at higher frequencies was just recently addressed in IEEE 1613.1 2013, which we'll talk about, and for the EMC testing of utility communications networking equipment. The trends in hardware are the miniaturization of devices, smaller gaps in the geometries inside their chips, lower power consumption for a longer battery life, which resulted in smaller voltage swings for the signals inside those chips, higher clock speeds, well above 3 gigs for modern PCs, and make them sensitive to shorter, smaller external events, wider bandwidth I/O ports, more susceptible allowing interference to enter the products, which results in increasingly vulnerable digital products. NIST SGIP formed the EMI Issues Working Group in September of 2010 to address equipment immunity testing and installed reliability for utility equipment. 8 months were allocated to develop some recommendations for the governing board. It took us 26 months. The EMI Issues Working Group report was white paper completed by November of 2012. IEC 61850-3, which was on the NIST Catalog of Standards, was the best practice guide that we use for determining which EMC tests to recommend for addition to IEEE 1613, which was coming up for renewal or amendment at that time. In addition, these 2 standards, 1613 and 61850-3, were already widely used in industry, as shown in their advertising. 61850-3 required these immunity tests, which are shown on the right, and addressed substation environments. 61000-4-6 conducted RF immunity. 61004-3 radiated RF immunity, which was covered here in IEEE under C37.90.2. 61000-4-8 power frequency magnetic fields. -10 damped oscillatory magnetic fields. -16 conducted common mode disturbances. 4-4 is electrical fast transit, which was already covered under C37.90.1 I mentioned earlier. 62104-5 surge. There was no indirect lightning test in the IEEE. And ringed and damped oscillatory waves were already covered by C37.90.1 based on 62104-12. These 5 gap immunity tests, which I just showed you in red, are referenced in the new 1613.1 2013. IEC 61850-3 invoked the test levels for substations products that were copied into the draft and called out for products used in Zone A, which was inside the substation fence. That's shown in the middle column here. Zone B is defined in IEEE 1613.1 as outside the substation fence out in the distribution network. That requires a lower test level in each case, taken from 61006-5, which was in our white paper. So the highest level inside the substation fence and 1 level lower everywhere else out in distribution. Any questions to here? Because now I'm going to go into those 5 tests along the left there. You see 5, 6, 8, 10, and 16. Any questions about the history or how we got here? IEC 61004-5 is surge immunity testing. Unidirectional overvoltages are caused by switching and lightning transients. Switching transients associated with major power system switching like cap banks, minor switching operations near instrumentation or load changes out in distribution, resonant circuits used with switching devices like thyristors, or short circuit arcing faults in the earthing system of the installations. Lightning transients are associated with direct lightning stroke to an external circuit, outdoors usually, indirect lightning stroke that induces voltage and currents on conductors, or earthing currents from nearby direct strikes coupled into the earthing network. I don't go into a lot of detail on Dash 5. You may have questions, or if you aren't familiar with the test, we can talk about that. I'll move on here to Dash 6, conducted RF immunity. This test simulates the interference from intended RF transmitters that are operating between 150 kilohertz and 80 megahertz. AEM is applied during the test. There are 4 coupling methods outlined in the standards. Coupling decoupling networks are the most likely to give the manufacturer a passing grade on this test. The other 3 coupling methods are no longer used because coupling decoupling networks now are available for all kinds of I/O lines, including Ethernet Cat5, which was the problem. So it's not in the manufacturer's interest to use any of these other direct injections, EM clamp, etc. Methodologies because they're more likely to fail the test. And if a coupler decoupler is available for their I/O line, and it probably is, all of them should be outfitted and terminated before testing begins on any of them. A level setting procedure requires that you set the level into that coupler decoupler for this setup. A drive table is generated. That's a frequency and an amplitude out of a signal generator. And that's played back with 80% AM modulation during the test while the EUT is monitored for its acceptance. This coupler-decoupler network level setting procedure is carried out with shorting adapters with 100 plus 50 ohms at each side or 300 ohm loop impedance. A 10 volt EMF level would mean that you would be looking for 17.4 dBm on the 50 ohm sensor shown on the left, connected to the power meter. This list of amplitudes, that's the frequency out of the signal generator and how many dBm it's putting out. There are 633 frequencies with 1% steps between 150 kilohertz and 80 meg. And that becomes the drive table that's played back during the run test. Before you decide to just play back those 633 frequencies at 3 seconds dwell, which will take about 34 minutes, you also need to investigate your clock frequencies and your multiples, harmonics of clock frequencies as well separately. So the test usually takes longer than that. Regardless, it is monitored for its acceptance to the criteria given in the 16.13 and 13.1 pair during the test. We'll talk about that later. Power frequency magnetic fields. 50 or 60 hertz magnetic fields testing simulates power frequency mag fields that come from nearby conductors or transformers that can upset power control systems. The standard recognizes 2 threats: steady fields from normal operating currents and higher amplitude short duration fields from fault currents. Level 5 severity testing is appropriate for equipment that's used in electrical plants. That's 100 amps per meter for 1 minute and 1,000 amps per meter for 3 seconds. Level 4 for use outside the substation. It's run by the immersion method. It requires that we rotate the coil or the EUT to all 3 axes, and then we rerun the test with a COM port or visual monitor like a camera, monitoring the EUT's acceptance on each axis, and then we verify the EUT still works. If it's a relay, it trips and resets. If it's something else, it's still functional. I didn't have to turn it off or on. I didn't have to do anything. It's self-recovered. Oscillatory magnetic field immunity testing to 61410 simulates magnetic fields that are generated by the switching of high voltage bus bars by isolators. Test mainly applies to equipment installed in high voltage substations at level 5 at 100 amps per meter in all 3 axes. Level 4 is used out in distribution, as those conductors out there still have this damped oscillatory fields on them, although at lower levels. The peak current from the oscillatory generator for the validation is set to usually 10 times the validation current. In other words, you would validate it at 1/10 of this, or 10 amps per meter field, resulting in 10 times the field strength, in this case 100 amps per meter. Current waveform into the loop antenna is validated and recorded for inclusion in the test report. Immunity conducted disturbances to .16. Conducted common mode disturbance testing simulates power electronic equipment, electrical plants, which generates frequency well above the mains. Standard addresses testing at DC, and then separately from 15 hertz to 150 kilohertz in common mode only. Substation equipment usually tests at level 4, that's a 30-volt EMF level. Audio amplifier is usually used for the first 3 segments up to about 15 kilohertz, and an RF amplifier is appropriate for testing from 15 kilohertz to as high as a megahertz, using 10% step sizes and a 10-second dwell time, while the acceptance of the EUT is assessed. And once again, you may also need to investigate other frequencies that are between those 10% step sizes if they're related to the operational frequencies inside the product. A 50 ohm test generator consists of a signal source connected to a power amplifier to the wall of the shielded enclosure. And inside, a 6 dB attenuator and cabling constitute the test generator. You begin testing by setting the signal source to 100 kilohertz, for instance, and adjust its level to achieve 30 volts open circuit. That's 15 volts terminated. That's 4.5 watts. That's 36.5 dBm measured on that power meter with a 40 dB pad protecting its sensor. There are a variety of networks you might be able to see in that ghosted image in the back, but I don't want to go into those too deeply. The idea here is that each of these networks is connected before testing begins on any of them, and you short their inputs. And then when you're ready to test on that port, you unshort the input and drive into it with this generator, which is a signal source amplifier and attenuator. The acceptance criteria in 1613.1, 2013, borrows from the earlier 1613, 2009. This has been adopted word for word in 61850-3 as well. The criteria applies for Class 1 devices where recovered disruptions are allowed, and Class 2 devices where no disruptions are allowed, which implies an optical fiber optic connection. No hardware damage, of course. No loss or corruption of stored memory or data, including the settings. The thing does not reset. Manual resetting is not required. The changes in the states of electrical, mechanical, or comm outputs are not supposed to occur, like alarms. No erroneous permanent change of the visual front panel of the thing. Momentary is okay. And the analog values shouldn't change by more than a couple of % full scale and have to revert later without intervention to the manufacturer claimed accuracy. IEEE 1613.1 extension to 1613 has a couple of other unique features. Communications cards inside smart meters will now be assessed using the IEEE 1613 acceptance criteria we just went over. The meters themselves were covered under ANSI C12.1, but there was no coverage of the cards, so this eliminated that gap. Extended radiated RF immunity testing has now been mandated up to 6 gigahertz with square wave, and lower than that, 3.8, I believe, gigahertz with AM modulation. And differential EFT coupling is only run now on DC power terminals at or above 48 volts, which simulates the switched armature coil back arcing across the floating station battery terminals, so that line balancing transformer, or balun, on the fast transient generator's output shown on the lower left there is still going to be required. This was a known source of disturbances that were originally addressed in C37.90.1, 2002. RFI hazards. Clause 7.3 of the document states that the wiring needs to be consistent with the manufacturer's recommended procedures, and the EUT We tested in its case with the covers and access doors in the closed position. You would think they'd learn. Owners of installed COM networking devices, like relays or other devices that communicate, may not have been aware of the hazards that exist when these covers or doors are open. We even talked about that incident in 2012, cell phones and tablets that can autonomously transmit without any action by the user. There has been evidence of misoperations, as I mentioned, by cell phones that are transmitted within 3 meters, about 10 feet of an open door on a networking device. So manufacturers are now encouraged by this clause to place warning labels on all their access doors and covers that alert the user that a misoperation may occur if they're left open, and that the phones or tablets shouldn't be allowed closer than 3 meters from those equipment. There's new work planned for the next revision to 1613.1, which was just finished in 2003. The IEEE Power and Energy Society Substation C2 Committee met first in January in 2014 in New Orleans. They met again recently. Consensus of the committee was to authorize a revision of 1613.1 that we had just finished, rather than make it into .2 or .3 or .4. So it will be another 1613.1, and they're going to expand the scope, which I believe we've just received, to cover additional autonomous utility equipment that does not communicate. This would be like capacitor bank controllers and tap changer controllers and data storage devices, displays, etc. The newly revised standard will apply the same tests and test levels to practically all utility equipment inside substations and out in distribution. We're still forming that working group, and work should begin later this year on that. Recently, going off my slide here, we just recently had a meeting of the Substations Committee, and they went over this again. The PAR is now approved, and the working group is forming. And we have 3 committees within the Power and Energy Society that are sponsoring new work on 1613.1 to expand its scope. And it would be the Substations Committee, the sponsor, and the Power Systems Relaying Committee, and the T&D Committee, which was a co-sponsor. So, also, we have a liaison back to the EMC Society of the IEEE, since the Power and Energy is writing an EMC document here. And this has been a successful model that was used in the original 1613.1 last year. So we're going to continue with that. Move this window away from the shared dash. It's pausing screen sharing. Uh-oh. Something happened. I don't know what that's doing. Anyway, I'd like to thank the IEEE Power and Energy Society Substation C2 Subcommittee Working Group on the 1613.1 extension, along with their chairman, John Tengen, for their enthusiasm in implementing these 5 gap immunity tests that were reported out by the SGIP EMI Issues Working Group. These efforts will finally lead to the harmonization for EMC testing for both European under the IEC and American under IEEE utility equipment in both transmission and distribution environments. So I want to thank you for listening, and that concludes my remarks for this morning.
Sorry, everybody. I think we're having some technical difficulties. Jerry, are you there? If anyone wants to send in some questions while we're waiting, you can do so now.
Hello.
Oh, are you back?
I am back. What happened
Okay.
there? I didn't get that.
Whoops. Okay.
Anyway, I hope you saw most of those slides.
Yep. We did. Where are you at, Jerry? Are you? Should we take a call for questions?
Sure. I can also go back and present these slides again if somebody. I can't hear anybody at this end.
No, all the attendees are muted. So, and we are getting responses from people that yes, they did see the slides. So, if you have anything, do you have anything more to present for anybody, or are we done?
We are done.
Okay, great. I have a couple questions. Why is the CDN the easiest to pass in 61,000 -4-6?
4-6. Good question. It's in the nature of the device itself. It's a coupling-decoupling network. That means it couples onto one side towards the EUT, and it decouples to the other side, which is the auxiliary equipment that's checking the EUT, are you okay, are you okay, are you okay, usually running a loop. So if you interfere with the auxiliary equipment, that decoupling network prevents that, or certainly minimizes the chances of it. So you can't tell when you're looking at your auxiliary equipment whether it's being interfered with or the EUT it's looking at is being interfered with. All you see is an error. So you tend to pass tests using the coupling-decoupling network, and you tend to not pass so easily not using it because your auxiliary equipment is more likely to be interfered with. And second of all, you're required by the standard to use a coupling-decoupling network, quote, if available, unquote. That means, does somebody make one? If they do, you're supposed to go buy it and put it on that I/O line. So you're supposed to use it, and that's why you're supposed to use it. Did that make sense?
Okay. We have another question.
Oh. It gets so quiet, I thought my phone died.
That's the thing with webinars. Sometimes there's a little bit of technical glitches, but I think we're okay now.
I promise not to hang up or do anything weird.
Okay, we have a few more. We have a few more questions. So the fail with other than CDN would be a false alarm?
Well, if you're going to a test lab that doesn't have a coupling-decoupling network for your I/O, make them buy one. Would be my suggestion, because you want to pass the test, and you also want to meet the document. 61,004-6 tells you in its decision matrix that you are to use a coupling-decoupling network if one is available, and it probably is. This is a voltage test. It's not like mill standard, where you inject current and monitor current. This is a voltage test. That's why it's spec'd as open circuit voltage in EMF. So it's a little bit different than the mill standard test, which is a current test. You inject interfering currents onto the I/O lines. That's not what's going on with -6. You supply interfering voltages onto the I/O lines using a level setting procedures to a coupling network, a coupling-decoupling network. Did I answer the question?
Okay. We have a few more. What recommendations do you have for monitoring equipment on I/O lines? Is there definitely anything not to use?
Oh, well, you don't want the auxiliary equipment to be interfered with in any of these immunity tests, which are simulations of actual interference signals being delivered to a product that makes it want to malfunction. So I really like small battery-operated fiber transceivers, where you have a length, 3-10 meters, an appropriate length of I/O wiring that you're going to inject on, which, how do you know it's appropriate? Because that's what your customer uses in the rack, 3 meters or 10 meters usually. And then go to a fiber transceiver floating on a piece of wood, powered with a battery. Now it can't be interfered with, and your auxiliary equipment is immune, and move it far away, 10, 15 feet away. So to prevent interference. So my favorite is fiber decoupling. These are not expensive. You can buy them from Shaxon, S-H-A-X-O-N, for decoupling lots of flavors of I/Os, including Ethernet and plain old telephone service, RG11, and serial ports, USB, and you name it.
Great, thank you. We'd like to have a call for final questions. If we have any more that anybody else would like to ask, we encourage you to send them now. I'd like to let you know that this recording will be on our site, emclive2014.com, shortly, if you want to check it out. We have EMC Live 2015 now scheduled for next year, April 28th to 30th. So if everybody likes these presentations, you can attend it once again. Last call for questions. If anybody has anything else they'd like to comment or question, if you don't have anything else, we will still accept them. You can email info@emclive2014.com. We could pass them along to Jerry. Otherwise, I think that we're at the end of our presentation. We'd like to thank Jerry for giving this informative lecture, and thanks everybody for attending.